Hello, and welcome back. We actually finished chapter 15 rather, in this video. The first video ran a little bit longer than I thought it would. As I said, I do want to kind of keep those videos timeline between 10 to 20 minutes, if at all possible. But it made for a good stopping point as well. So if we get to the last sort of section of this chapter, a skill we want to be able to learn is to learn how to predict precipitation events. In other words, for example, if we have a lead 2 chloride solution, and we're told that we have in the particular solution that current lead concentrations are 0.1 molar and current chloride concentrations are 0.05 molar, under those conditions, do we expect a precipitate to form? And the idea we're going to use is we're going to calculate QSP. We're going to calculate that reaction quotient, the same reaction quotient we've calculated earlier for other types of equilibria. And as before, we're going to compare that to KSP. And the kinds of conclusions we're going to draw in this particular context will be exactly the same as we would have for any other equilibria. Specifically, if QSP that we calculate is less than the KSP at that temperature, and that means the equilibrium will shift to the right. Shift to the right with solubility equilibria means presence of ions, which means that we've not yet saturated the solution, which means that no precipitate should form. But the opposite is true, that if QSP is greater than KSP, that means the equilibrium will shift to the left, and shift to the left means the presence of a solid substance. So to see that in action with this particular example, and then we'll do a slightly more complicated example here on the next slide. So we have our 0.1 molar lead concentration, and we have a 0.05 molar chloride concentration, and we want to determine under these conditions whether or not a precipitate will form. So to do that, we'll calculate QSP. We call QSP as the same expression as KSP. So it's concentration of the products raised to their respective coefficients. So lead to the first power times chloride concentration to the second power. The only difference, of course, is that we calculate QSP under any conditions, whereas KSP, this number is only true when we have a saturated solution. So in this case, I can simply plug in my values. So QSP is equal to concentration of lead, because I'm told directly what that concentration actually is, times concentration of chloride, squared. And when I plug those numbers in, 0.1 molar times 0.05 molar squared, I get a value of 2.5 times 10 minus 4. So then all remains is then compare my QSP to the KSP. And we see that in this case, our QSP, 2.5 times 10 to the minus 4, is greater than the KSP of 1.2 times 10 to the minus 5. So because QSP is greater than KSP, that means the equilibrium shift to the left, which means we do expect a precipitate to form under those conditions. So when you're given the concentrations of the ions in solution, then we can directly plug those numbers into our QSP expression, and then compare that to KSP to decide whether or not a precipitate is going to form under those conditions. The second example is a little bit more complicated. Here we have the same lead 2 chloride. This time we're not told directly what the concentrations are of the lead ions and chloride ions in the solution, but we're told how the solution was made. That 100 milliliters of 0.08 molar lead 2 nitrate solution was mixed with 250 milliliters of a 0.03 molar sodium chloride solution. And the question is, under those particular circumstances, will a precipitate of lead 2 chloride form? So our overall goal is still to calculate QSP. We still want to calculate the product of the concentration of lead times concentration of chloride squared. And then as the first example, compare that to KSP to decide whether or not precipitate is going to form. The difference here is, though, that we're not given what these concentrations are, or they're given how the solution was mixed, how the solution was made. So we first need to calculate what the concentration of lead is in my solution after the mixing, as well as concentration of chloride in my mixture after the mixing. And so to do that, because we're combining two liquids, we can calculate the concentration of any of these ions using our dilution equation. And so for the lead, concentration of lead in my solution, that's going to be equal to the product of the concentration, the volume and the concentration. So this is your, so essentially dilution equation, because like your C1V1 equals C2V2, and we're calculating C2, the concentration of the substance after the mixing has occurred. That's going to be equal to C1V1 over V2, where C1, V1 are the original concentrations and volumes respectively, and then V2 is the new volume after the mixture, after the two substances have been combined. So the concentration of lead is going to be equal to C1, so that's equal to our 0.08 moles per liter lead times V1, 100 milliliters, divided by the new volume. The new volume is going to be 250 milliliters plus 100 milliliters, or a total volume of 350 milliliters. Our new concentration of lead, the actual concentration of lead in our solution after the mixing has occurred, is going to be 0.0229. So that's the number we'll plug in to our lead concentration. Likewise with the chloride, same idea. Chloride concentration is equal to its concentration originally, which is 0.03 molar, times its original volume, divided by the new volume, which is still the same, 350 milliliters. So we get a concentration of chloride of 0.03 times 250 divided by 350, or about 0.0214. And that then will be the concentration of chloride we plug into our QSP expression. So if we then calculate our QSP, now that we know what the concentrations of lead and chloride are in my solution, concentration of lead is 0.0229 molar, concentration of chloride is 0.0214 molar squared, and that product is 0.0229 times 0.0214 squared, or about 1.05 times 10 to minus 5. About 1.05 times 10 to the minus 5. So that's my QSP. And then as before, we can compare our QSP to our KSP. So as under these conditions, they're both to the -5. So then our QSP, 1 times 10 minus 5, is less than our KSP of 1.2 times 10 minus 5. So under these conditions, because QSP is less than KSP, equilibrium will shift to the right, which means it'll shift towards the products, the ions. And so under these conditions, we don't expect a precipitate to form. It's very close, so it won't take much more of either the lead or the chloride for precipitate to form, but currently we are underneath that critical value. And finally, the last calculation we want to do to finish up this chapter is this example, where we're given the amount of one of the ions in a solution, 0.052 molar, and presumably there's another source, there's separate sources of silver ions and phosphate ions. So under these conditions, at what minimal phosphate ion concentration do we expect a silver phosphate precipitate to form? So this is our picture where we know we have the silver concentration is 0.052 molar. We want to find the concentration of phosphate in which we expect to see a precipitate forming. So we know a precipitate is going to form when QSP is greater than KSP. And KSP is our 9.1 times 10 minus 14 for the substance. So our QSP expression is concentration of silver, which we know, cubed times concentration of phosphate, which we don't know. So that product, in order for precipitated form, has to be greater than the KSP, so that product has to be greater than 9.1 times 10 to the minus 14. So we plug in what we know, solve what we don't know. So we know the concentration of silver is 0.052. We cube that, and we multiply that by our unknown concentration of phosphate, just X. That has to be greater than 9.1 times 10 minus 14. 0.052 cubed is 1.41 times 10 minus 4 times concentration of phosphate. That has to be greater than 9.1 times 10 minus 14. And finally, divide both sides by 1.41 times 10 minus 14. We find that X, which is our minimal phosphate concentration in order for precipitation to occur, must be greater than 9.1 times 10 minus 14 divided by 1.41 times 10 minus 4, or about 6.5 or so, 6.5 times 10 to the minus 10 molar. So that's the minimal phosphate concentration needed in order for precipitated form under these conditions. And with that, we finally finish our chapter 15. Next time, we'll start a new chapter, chapter 16, which gets into the question of, will a reaction occur? Thermodynamics and other aspects of that.